If our objective is to keep the mean squared estimation error small, then the best possible estimator is the conditional expectation. But sometimes the conditional expectation is hard to calculate. Maybe we're missing the details of the various probability distributions. Or maybe we have all the distributions that we need, but the formulas are complicated. After all, the conditional expectation can be a complicated nonlinear function of the observations. For this reason, we may want to consider an estimator that has a simpler structure, an estimator that is a linear function of the data. And then, within this class of estimators, find the one that results in the smallest possible mean squared error. In this lecture, we will formulate this linear least squares estimation problem and then solve it. We will see that the solution is given by a simple formula that involves only the means, variances, and covariances of the random variables involved. Because of the simplicity of the method, linear estimators are used quite often, especially in systems where estimates need to be computed quickly in real time as observations are obtained. We will look into some of the mathematical properties of the linear least mean squares estimator and the associated mean squared error, revisit an example from the previous lecture, and finally close with some comments on the ways that this estimator can be used.
Let us now introduce the linear least mean squares formulation. The setting is the usual one. We have an unknown random variable and another random variable, which is our observation. We are given enough information so that we can, for example, calculate the joint distribution of these two random variables. What we would like to do in the least squares methodology is to come up with an estimator such that the mean squared error of this estimator is as small as possible. And we have seen the general solution to this problem. If we consider arbitrary estimators, it turns out that the best possible estimator, the best possible function g, is this particular function of the observations. Our estimator is the conditional expectation of theta given x. Now let us look at an example that we considered earlier. Suppose that x and theta have a joint PDF which is uniform over this particular region. We did consider this example and we found that the optimal estimator was a function that had this particular shape. So this blue curve here corresponds to the function which is the conditional expectation of theta given the value of the observation that we have obtained. We notice that this function is nonlinear, but it is only mildly nonlinear. The fact that it is nonlinear is a little bit of a nuisance. It makes it somewhat of a complicated function. Wouldn't it be nicer if our estimator had turned out to be a linear function of the data, such as this one? It would have been nicer, but unfortunately, that's not the case. But what if we impose it as a constraint that we will only look at estimators that are linear functions of the data? What does that mean? Mathematically speaking, it means that we will only consider estimators that depend linearly on the data x. Now, a and b here are some parameters that are for us to choose. If I choose a and b differently, I'm going to get a different red curve here. Which one is the best red curve? Well, we need a criterion, but let us stick to our mean squared error criterion, and in that case, we are led to the following formulation. We want to find choices for a and b. That is, we want to choose a particular red line so that the resulting estimation error, the resulting mean squared estimation error, is small as possible. So what we have here is the random variable. Here is the value that's going to be given to us by our estimator, and we look at the associated error, square it, and take the expectation. So this is the linear least mean squares formulation. We're looking for an estimator which is a linear function of the data, and we want to choose the best possible linear function. How does it compare to the earlier problem of picking the best estimator? Here we were considering an arbitrary function g, and we were trying to find the best possible function of the data, which would be our estimator. So this was really an optimization over all possible functions. Here we only have an optimization with respect to two numbers. So at least mathematically this should be a simpler problem, and we will see that it has a simple solution. Before going on to the solution, however, let me make one comment that in some cases the linear least squares estimation problem is relatively easy to solve, and these are the cases where the conditional expectation turns out to be linear in the data. This is the best possible estimator. If it happens to be linear, it's at least as good as any other linear estimator, so it's also going to be the optimal linear estimator. That is, if the optimal solution turns out to be already linear, by imposing the extra constraint of sticking to linear estimators is not going to make any difference. But for the general case, in general, this is not going to be the case. The conditional expectation may well turn out to be a nonlinear function of the data, as in this example, and in those cases, the linear least mean squares estimator is going to turn out to be different. We will now develop the solution to the linear least mean squares estimation problem. We want to find coefficients a and b that make this expression, this mean squared error, as small as possible. We will approach this problem by proceeding in two stages. In the first stage, we assume that the choice of a has already been found and concentrate on the question of choosing b. Now, if a has been found and has been fixed to a specific number, then this quantity here is a specific random variable. And what do we have? We have a random variable minus a constant, and we want to choose that constant so that this difference squared is as small as possible in the expected value sense. So essentially, we're trying to choose a constant b that estimates this random variable in the best possible way. But this is a problem that's familiar to us, and we know that the best choice of b is equal to the expected value of that random variable. And using also linearity, this expected value can be written in this form. So if we know A, this is how B should be chosen. Let us now move on to the choice of A. Since we know what B should be equal to, we can rewrite this expression that we're trying to minimize by substituting our choice of B, which is the expected value of theta minus ax. And this is the quantity we want to minimize. What is it? We have a random variable minus the expected value of that random variable squared, and then we take expected value. This is just the variance of the random variable theta minus ax. This is the variance of the difference of two random variables. Because the two random variables are dependent, this is not just the sum of the individual variances, but we do have a formula even for the general case, and the formula tells us that the variance of the difference of two random variables is the variance of the first random variable plus the variance of the second, and when we pull a outside the variance, that gives us a contribution of a squared. And then we have a cross term. Because of the minus sign here, the cross term will have a minus sign. We have a factor of 2. And then we want the covariance of theta with ax. And because we have seen that covariances behave in a linear manner, we can pull a outside the covariance, and this is what we are left with. This is the quantity we want to optimize with respect to a. And to do this optimization, we just set the derivative with respect to a to 0, and that's going to give us 2a times the variance of x minus twice the covariance of theta with x equal to 0, from which it follows that A should be equal to the covariance of theta with x divided by the variance of x. So we have found what A should be. Once we know what A is, we know what B should be equal to, so we have solved the problem, and here's the form of the solution. This coefficient here is the coefficient A, so we have here the term AX, and then this term together with A times the expected value of x, these correspond to the coefficient B. It's also instructive to rewrite this solution in a slightly different form involving the correlation coefficient. Recall that the correlation coefficient between two random variables is defined as the covariance between the two random variables divided by the product of their standard deviations. Using this relation, we can now write the coefficient A as the covariance, which is rho times sigma theta sigma x, divided by the variance of x, which is sigma x squared. And after we cancel a factor of sigma x from the numerator and the denominator, we see that A is also equal to rho times sigma theta divided by sigma x, and this gives us this alternative form for the solution. What we will be doing next will be to interpret this solution and also to give a number of examples. Now that we have found the solution to the linear least mean squares estimation problem, it is time to offer a few comments, make some observations, and provide some insights. A first important observation is the following. In order to implement this estimator, you do not really need to know everything about the distribution of x and theta. The only thing that you need to know is the mean of the two random variables that are involved, the variance of x, and the covariance of theta with x. So it's only a few pieces of information that we need, and that means that we do not need to be so careful about modeling in a particular problem, as long as we know what the means, variances, and covariances are. This is a very desirable property because it tells us that this could be simpler to implement in the real world. Now let us start looking at the form of the solution, and let's try to give some interpretation. Suppose that the correlation coefficient is positive. Then what does this estimator do? It starts with a baseline estimate, which is the expected value of theta, and then provides us with a correction term that's based on the data. In particular, if it happens that we see an observation that's larger than expected, in that case, our estimate is going to be above the expected value of theta. So we start with our baseline estimate, but if we get a big observation, then our estimate will also be large. And conversely, if x happened to be on the lower side, below the expected value, then our estimate would also be below the expected value of theta. Of course, there's an analogous story. If rho was negative, then the same argument would apply, except that it would work in the opposite direction. When rho is negative, if we see a large x, then we will come up with a low estimate for theta. Let us look at another special case now. Suppose that rho is equal to 0. X and theta are uncorrelated. Then this last term here disappears, and in this case our estimate is going to be just the expected value of theta. In other words, our estimate doesn't make any use of the data. Essentially what's happening is that a linear estimator exploits the correlation between the two random variables to come up with an estimate. But if the two random variables are uncorrelated, then it's nothing that it can do, and it does not give us anything useful. It just reports back the expected value of theta. Let us now look at the mean squared error that's obtained when we implement this linear estimator. Let us write down what this expression is. And to keep things simple, let us assume that we have zero means and zero variances. So just for the purposes of this derivation and to simplify the algebra, we will work with the zero mean case. So in this case, what we have, let me first write theta and then put here the estimator. The estimator is rho times sigma theta sigma x times x. Basically, I took this formula, but I put zeros for the expected values. Now let us expand this quadratic. We obtain the expected value of theta squared. That's the variance of theta, since we assumed zero means, and the variance is the square of the standard deviation. Then we have a cross term. It's going to be twice the expectation of the product of theta with this. Now we can take out this constant outside the expectation, so it's 2 rho sigma theta sigma x. And then we are going to have the expected value of theta times x. Because we assumed zero means, the expected value of theta times x is the covariance of theta and x, and the covariance is rho sigma theta sigma x. And finally, we have a last term, which is rho squared sigma theta squared divided by sigma x squared times x squared. We have an expected value, so that's the expected value of x squared, which is just the variance of x, or sigma x squared. Okay, this looks like a big mess, but in fact we get nice cancellations. This term cancels with that term. This term cancels with that term. We notice that we have sigma theta squared in each one of those terms, so we can factor them out. And then here we have minus 2 rho squared plus rho squared. When we subtract those two terms, we're left just with a minus rho squared term. So after you do that algebra carefully, you find that the answer takes a very simple form. It's 1 minus rho squared times the variance of theta. I should add here that this formula remains valid even without the assumption that x and theta have zero means. What's the interpretation of this? The variance of theta describes the initial uncertainty we have about theta. But after we carry out the estimation, the uncertainty gets reduced. And it gets reduced by a certain factor. What is this factor? If rho is equal to 0, then this coefficient is 1 and we do not have any variance reduction. After all, when rho is equal to 0, this estimator is not very useful. It doesn't help us estimate theta better, so the expected value of the squared error is the same as the variance of theta. On the other hand, when rho is large, then this term here becomes small, and it means that the mean squared error is small. In fact, there is an extreme case that's interesting, namely if rho is equal to 1 in absolute value, so if the random variables are perfectly correlated, then this term here becomes 0, and the mean squared estimation error is 0, which essentially means that our estimate is going to be equal to the unknown value. So the special case of a unit correlation in absolute value corresponds to a case where we can perfectly estimate theta using a linear estimator. So to summarize, the correlation coefficient plays a crucial role in linear least squares estimation. It determines the form of the estimator, and also it determines how much the uncertainty in theta will be reduced through the process of estimation. Let us now illustrate the linear least mean squares estimation methodology in the context of an example, and we're going to revisit our familiar example that we considered earlier in the context of general least mean squares estimation. Let us remind ourselves what were the assumptions behind this example. There is an unknown random variable that we wish to estimate, and that random variable happens to be uniform on a range from 4 to 10. What we get to observe is a random variable x, which is equal to theta plus or minus something. So x is theta plus a noise term, and that noise term can be anything in the range from -1 to +1. Furthermore, the distribution of u is this particular uniform no matter what theta is, so theta and u are independent. These modeling assumptions correspond to this picture. This is the range of x and theta, and the joint distribution of x and theta happens to be a uniform distribution on this particular shape. However, we're not really going to use this picture other than for illustration purposes. You could take just this as the formulation of the problem that we're interested in. So now, to develop the form of the optimal linear estimator, all we need to do is to determine the various constants that show up. So let's start with expectations. Theta is uniform from 4 to 10, therefore the expected value is the midpoint, which is equal to 7. U has a symmetric distribution around 0, so its expected value is going to be equal to 0. X is the sum of theta and u, therefore its expected value is the sum of these two expected values and is equal to 7. Let us now look at variances. The variance of a uniform is equal to the square of the length of the interval on which the uniform is distributed, in this case it's 6 squared, divided always by a coefficient of 12. 6 squared is 36, so we obtain 3. The variance of u is determined by a similar formula, except that now we have an interval of length 2, so we obtain 2 squared over 12, and this is 1/3. Now let us look at the variance of x. Since x is the sum of theta and u, and since the two of them are independent, the variance of x is going to be the sum of these two variances, which is 10 over 3. Now let us try to calculate the covariance term. The covariance of theta with x is this expression, because x is theta plus u. And then using linearity properties of covariances, this is the covariance of theta with itself plus the covariance of theta with u. Now theta and u are independent, so this covariance is equal to 0. The covariance of theta with itself is just the same as the variance, so here we obtain an answer of 3. And so now we have all the pieces of information that we need, and we can proceed and write down the form of the linear estimator. The expected value of theta is 7. Then the covariance of theta with x is 3, divided by the variance, which is 10 over 3. So this ratio becomes 9/10. And then x minus the expected value of x gives us this term. So this is the form of the optimal linear estimator, and if you wish to plot it, it is a curve of this kind. It is actually interesting to contrast this solution to the shape of the optimal estimator, the least mean squares estimator, or the conditional expectation estimator, which we had found earlier and which corresponds to this particular blue curve. So in some sense, the linear estimator is a pretty good approximation of the optimal nonlinear one. It does the best job that it can do, subject to the constraint that it has to be a linear function. Notice also that this coefficient here is of course positive. This reflects the fact that the two random variables, x and theta, are positively correlated. This should be clear from this diagram. When x increases, theta tends to also increase and vice versa. It's also reflected in the fact that the covariance is a positive number. On the other hand, because this coefficient is 9/10 and not equal to 1, this red line is somewhat slanted in comparison with the orientation of the diagram that we have. The calculations that we went through in this particular example are pretty generic. This is what you need to do in general. You just look at the random variables involved, you calculate their means, you calculate their variances, then you may have to do some extra work to calculate the covariance of interest, and once you're done, you plug in the numerical values that you have found, and you obtain the form of the linear estimator. Let us now go through another example which will be a little more challenging. We're going to revisit an old problem. We have a coin that has an unknown bias, theta, and we have a prior distribution on this theta. We fix some positive integer n, we flip a coin n times that has this unknown bias, and we record the number of heads. On the basis of the number of heads that have been observed, we wish to estimate the bias theta of the coin. To make things more concrete, we're going to assume a prior distribution on theta that is uniform on the unit interval. Now, this is a problem that we have considered before. We have calculated the expected value of theta given x, and we did find that the expected value takes this particular form. Now, notice that this is a linear function of x. And if it turns out that the least mean squares estimator is a linear function of x, then we're guaranteed, since this is the best, that this is also the best within the class of linear estimators. So we immediately have the conclusion that the linear least mean squares estimator is this particular function of x. So there's not much left to do. On the other hand, just for practice, let us derive this answer directly from the formulas that we have for the linear least mean squares estimator and see whether we're going to get the same answer. So we want to use this formula. And in order to apply this formula, all that we have to do is to calculate these expected values, these variance, and this covariance. So now let us move on to this particular calculational exercise. Let us start by writing down what we know about the random variables involved in this problem. About theta, we know that it is uniform, and so that it has a mean of 1/2 and a variance of 1/12. About x, what we know is the following. If you fix the bias of the coin, then the number of heads you are going to obtain in n flips has a binomial distribution with parameters n and theta. But of course, theta itself is a random variable, so for this reason, this is a conditional distribution. But within the conditional universe, we know the mean and the variance of a binomial, and they are as follows. The mean of a binomial is n times the bias of the coin. But because we're talking about a conditional universe, this is a conditional expectation, and it's a random variable because it's affected by the value of the random variable theta. And similarly for the variance, it's the usual formula for the variance of a binomial, except that now the bias itself is a random variable. So now let us continue with the calculation of the quantities that we need for the formula for our estimator. Let's start with the expected value of x. Since we know the conditional expectation of x, we can use the law of iterated expectations. The unconditional expectation is the expected value of the conditional expectation, which is n times theta. And since the mean of theta is 1/2, we obtain n over 2. Let us now continue with the calculation of the variance. There are different ways that we can calculate it. One could be the law of total variance, but we will take the alternative approach, which is to use the general formula for the variance, that the variance is equal to the expected value of the square of a random variable minus the square of the expected value. We know the expected value of x, so all that's left is to calculate the expected value of x squared. How are we going to calculate it? Well, we know the conditional distribution of x, so it should be easy to calculate the conditional expectation of x squared in the conditional universe, and then use the law of iterated expectations to obtain the unconditional expectation. So now we need to calculate this conditional expectation here. How do we do it? The expected value of a square of a random variable is always equal to the variance of that random variable plus the square of the expected value. We're going to use this property, but we're going to use it in the conditional universe. So in the conditional universe, this is going to be equal to the variance in the conditional universe, which is n times theta times 1 minus theta, plus the square of the expected value of x, but the expected value in the conditional universe, which is this quantity, n times theta. So we obtain another term, n squared, theta squared. So now we can go back to our previous calculation and write here the expected value of this expression, which is n times theta, and then we have some theta squared terms. One is n squared, the other is a minus n, so we obtain plus n squared minus n theta squared. The expected value of n times theta is n times the expected value of theta, which is 1/2. So we obtain a factor of n over 2. But then we have this additional term here. We need the expected value of theta squared. What is it? Well, since we know the mean and the variance of theta, we can calculate the expected value of theta squared. It is equal to the variance plus the square of the mean, and this evaluates to 1/3. So from here we're going to obtain plus n squared minus n divided by 3. And you can rewrite this term in a different way by collecting first the n terms, n over 2 minus n over 3. This gives us n over 6. And then there's the n squared term, which is n squared over 3. Now that we found the expected value of x squared, we can go back to this calculation. We have n over 6 plus n squared over 3 minus the square of the expected value of x, which is this expression here, so we obtain minus n squared over 4. 1/3 minus 1/4, that makes 1/12. So we obtain n over 6 plus n squared over 12. Or another way of writing this is n times n plus 2 over 12. And this completes the calculation of the variance of x. The last quantity that's left for us to calculate is the covariance of theta with x. We're going to calculate it using the alternative formula for the covariance, which is the expectation of the product minus the product of the expectations. We have the expectations, but we do not have the expectation of the product, so we need to calculate it. Once more, it's going to be the same trick. We're going to condition on theta and then use the law of iterated expectations. So the law of iterated expectations, when you condition on theta, takes this form. And to continue here, we need to find this conditional expectation in the inside. This conditional expectation, what is it? If I give you theta, then you know theta. It is becoming now a constant. There's nothing random to it. So it can be pulled outside the expectation. And we obtain theta times the conditional expectation of x. We know what the conditional expectation of x is. It's n times theta. So from here we obtain overall a term n times theta squared. So now we can go back here. We have the expected value and the term in the inside. We just found it. It's n times theta squared. And since the expected value of theta squared is 1/3, from here we obtain n over 3. And now we can go back finally to the calculation of the covariance. It's going to be n over 3 minus the expected value of theta, which is 1/2, times the expected value of x, which is n over 2. So it's minus n over 4, and this evaluates to n over 12. So we have succeeded in calculating all the quantities that are needed in the formula for the linear least mean squares estimator. We can now take those values that we have just found and substitute them in this formula. And after a little bit of algebra and moving terms around, everything simplifies to this expression. Just to verify that this makes sense, what is the coefficient next to x? It's the covariance divided by the variance. N over 12 divided by this expression. This n cancels that n, this 12 cancels that 12. We're left with an n plus 2 in the denominator. And indeed, the coefficient that multiplies x is the term n plus 2 in the denominator. And you can similarly verify that the constant term as well is the correct one. So, of course, this answer is what we had found in the past to be the optimal, the least mean squares estimator of x. As we discussed earlier, when this is linear in x, it has to be the same as the linear least mean squares estimator. So this answer is not a surprise, but it was an interesting and perhaps useful exercise to go through the details of this calculation to see what it takes to figure out the different terms in this formula. We have presented the complete solution to the linear least mean squares estimation problem when we want to estimate a certain unknown random variable on the basis of a different random variable x that we get to observe. But what if we have multiple observations? What would be the analogous formulation of the problem? Here is the idea. Once more, we restrict ourselves to estimators that are linear functions of the data, linear functions of the observations that we have. And then we pose the problem on finding the best choices of these coefficients a1 up to an and b. What does it mean to find the best choices? It means that if we fix certain choices, we obtain an estimator, we look at the difference between the estimator and the quantity we're trying to estimate, take the square, and then take the expectation. So once more, we're looking at the mean squared error of our estimator, and we try to make it as small as possible. So this is a well-defined optimization problem. We have a quantity, which is a function of certain parameters, and we wish to find the choices for those parameters or those coefficients that will make this quantity as small as possible. One first comment is similar to the case where we had a single measurement, is the following. If it turns out that the conditional expectation of theta given all the data that we have is linear in x, if it is of this form, then what happens? We know that this is the best possible estimator. If it is also linear, then it is the best estimator within the class of linear estimators as well. And therefore, the linear least mean squares estimator is the same as the general least mean squares estimator. So if for some problems it turns out that this is linear, then we automatically also have the optimal linear estimator. And this is going to be the case once more for certain normal problems with a linear structure of the type that we have studied earlier. Now let us look into what it takes to carry out this optimization. If we had a single observation, then we have seen a closed form formula, a fairly simple formula that tells us what the coefficients should be. For the more general case, formulas would not be as simple, but we can make the following observations. If you take this expression and expand it, it's going to have a bunch of terms. For example, it's going to have a term of the form a1 squared times the expected value of x1 squared. It's going to have a term such as twice a1 a2 times the expected value of x1 x2. And then there's going to be many more terms. Some of them will also involve products of theta with this. So we might see that we have a term of the form a1 expected value of x1 theta. And then there's going to be many more terms. What's the important thing to notice? That this expression as a function of the coefficient involves terms either of this kind or of this kind or of that kind, first order or second order terms. To minimize this expression, we're going to take the derivative of this and set it equal to 0. When you take the derivative of a function that involves only quadratic and linear terms, you get something that's linear in the coefficients. The conclusion out of all this discussion is that when you actually go and carry out this minimization by setting derivatives to 0, what you will end up doing is solving a system of linear equations in the coefficients that you're trying to determine. And why is this interesting? Well, it is because if you actually want to carry out this minimization, all you need to do is to solve a linear system, which is easily done on a computer. The next observation is that this expression only involves expectations of various terms that are second order in the random variables involved. So it involves the expected value of x1 squared, it involves this term which has something to do with the covariance of x1 and x2, this term that has something to do with the covariance of x1 with theta. But these are all the only terms out of the distribution of the x's and the thetas that will matter. So similar to the case where we had a single observation, in order to solve this problem, we do not need to know the complete distribution of the x's and of theta. It is enough to know all the means, variances, and covariances of the random variables that are involved. And once more, this makes this approach to estimation a practical one because we do not need to model in complete detail the distribution of the different random variables. Finally, if we do not have just one unknown random variable, but we have multiple random variables that we want to estimate, what should we do? Well, this is pretty simple. You just apply this estimation methodology to each one of the unknown random variables separately. To conclude, this linear estimation methodology applies also to the case where you have multiple observations. You need to solve a certain computational problem in order to find the structure of the best linear estimator, but it is not a very difficult computational problem because all that it involves is to minimize a quadratic function of the coefficients that you are trying to determine, and this leads us to having to solve a system of linear equations. For all these reasons, linear estimation or estimation using linear estimators is quite practical. As we discussed earlier, even if we have multiple observations, we can still find the structure of the best linear estimator in a fairly simple computational way by solving a system of linear equations. But usually we do not get nice and simple formulas. But here is a nice example in which we will get a simple formula. The example is something that we have seen before in various guises. We're trying to estimate a certain quantity theta, and what we obtain is multiple noisy observations of theta. That is, at each observation we see theta plus a noise term. The assumptions that we make is that theta has a prior distribution with a certain mean and a certain variance, and the noise terms are zero mean, but they have some variance. And the additional assumption that we make is that all these random variables are independent of each other. So the noise terms are independent between themselves, and also the noise terms are independent of theta. This is the usual assumption, but actually in the linear estimation problem we do not need to make an independence assumption. It's enough for our purposes to just assume that they are uncorrelated. So we will assume that the correlation coefficient between any two of these random variables is equal to 0. Now we can write down the form of the mean squared estimation error criterion that we have and try to find good choices for the coefficients to be attached to each one of the observations. However, we're going to find the solution to this problem using a shortcut that's going to bypass all kinds of computations. Here's the trick. Let us suppose, in addition, that these random variables were not just uncorrelated, but independent, and that they happened to be normal random variables. This is a problem that we did study before, and we did find the maximum a posteriori probability estimate of theta. Because the posterior was normal, we found that this was also the conditional expectation estimator of theta, and we did find a formula for it, which took this form. This was the form of the optimal estimate of theta if you obtain values for the different observations, little xi. On the other hand, if you want to translate this into random variable notation, then notice that this is going to be a random variable. This is our estimator. It's the conditional expectation of theta given x, and it's random because it depends on the values of the data that we see, which are themselves random variables. On the other hand, this x0 is actually the prior mean of theta, so this is a constant, it's not random, and that's why we keep it with a lowercase notation. Now, what is interesting about this form? It is a linear function of the observations. And as we have discussed earlier, if it turns out that the conditional expectation is linear in the observations, then this is also the best possible linear estimator. So for the special case where our random variables are independent and normal, we have a formula for the best linear estimator. Now, what if they are not normal? Suppose that they are not normal, but that they have the same means and variances as here, as in the normal example. Since these means and variances are the same, and since these random variables are uncorrelated, it follows that also all kinds of covariances between the random variables involved here are going to be the same as for the normal example. Now, the optimal solution to the linear estimation problem, as we discussed earlier, only cares about the means, variances, and covariances of the random variables involved. The details of the distribution do not matter. So, whether we have normal distributions or non-normal distributions, as long as we're making enough assumptions that fix all the means, variances, and covariances of interest, we should be getting exactly the same solution. Therefore, this solution remains valid for the case of general random variables as well. In this final segment, we want to discuss an interesting point about linear estimators. Here's what the issue is. You obtain an observation x on the basis of which you want to estimate theta. But perhaps you measure x on a different scale, let's say on a cubic scale, so that what you record actually is x cubed. So you're faced with two possible estimation problems. One estimation problem is to use x to estimate theta. Another estimation problem is to use x cubed to estimate theta. Does it make a difference? Let us consider the case of least mean squares estimation without any linearity constraint. If you use x to estimate theta, your estimator is going to be this conditional expectation. If you use x cubed to estimate theta, your estimator will be this conditional expectation. Are they different? Well, x and x cubed carry the same information about theta. In particular, the posterior distribution of theta given x is going to be the same as the posterior distribution of theta given x cubed. You will be getting the same information, the same knowledge about x. And in particular, if you calculate conditional expectations, these will also be the same. What about the linear case? If we restrict to linear estimators, then on the basis of x, you would form a linear estimation of this kind. But if your observation is in the form of x cubed, then a linear estimator would form a linear function of x cubed. So this would be a different kind of estimator. We have seen a formula on how to obtain the best estimator, the best choices of A and B for estimators of this kind. We can use that same formula to obtain the best estimator of that kind. It's going to be, of course, a different estimator. Here we're optimizing within a different class. Which one of the two is better? Well, this depends on what you know about the particular problem at hand. If you have some reason to believe, or if you know that theta and x are roughly related by some kind of cubic relation, then perhaps estimators in this class are going to perform better than estimators in that class. Let me also point out a related issue that would come here. To find the right choice of A, you need to know the covariance between x and theta. That's what the formula tells us about the optimal linear estimator. Here, you would need to know the covariance between theta and x cubed. In addition, the formula requires the variance of x, but here instead of x we're using x cubed, so in this case we would need the variance of x cubed. Now, this could be more challenging. In general, the higher the powers that you have, the more difficult these quantities are to calculate or to know what they are. But leaving that issue aside, what we have here is two alternative choices for the structure of the estimator that we are using. Now we can push this story further. Instead of considering just estimators of this kind, we might consider as well estimators of this kind. Is this a linear estimator? We still call it a linear estimator because it is linear in the coefficients that we have to choose on how to optimize. That's the more important part. It's the linearity in these coefficients that's important rather than the linearity in the x's. So as a function of x, this is nonlinear. On the other hand, we can think of this x as one observation, x squared as another observation, x cubed as a third observation, and what we got here is a linear function of three different observations. So we can still pose a least squares problem in which we try to find the best choices for the coefficients a1, a2 and a3 as well as the coefficient b, find those choices that are going to give us the smallest possible mean squared error. So we can optimize within this class. Within this class of estimators, we certainly have more flexibility. This is a more general class of estimators than either this one or that one, so within this class we should be able to do even better. On the other hand, we will have to pay a price that this is a more complex structure. It will be more difficult to find the optimal coefficients, and also we're going to need higher order moments or expectations related to the x's and the thetas. Finally, there's nothing special in us using powers of x and using a polynomial. We could also look at estimators that have some other type of structure. For example, we might want to mix an exponential function in x and a logarithmic function of x, look at estimators of this form, and try to choose the best one, find the best choice of the coefficients. Again, this is something that is possible. And again, it's going to boil down to solving a system of linear equations in the coefficients. On the other hand, we need to know various expectations about x that might be difficult to obtain. How do we choose which structure to use? Should it be this one, this one, this one, or that one? There's a trade-off that more complicated structures introduce more complexity and make the problem more difficult. But there's also another issue. It has to do with what we know about the particular problem at hand. If we know or have reason to believe that third-order polynomials are going to give us excellent estimates of theta, then we may want to work within this class. In any case, the moral of the story is that if we are to use the linear estimation methodology, we do have some choices. Linear in what? And different choices will give us different performance. But this now gets somewhat away from the subject of a mathematical methodology, and it gets closer to the art that you need to exercise in any particular problem domain.